We'll present the state of privacy payment protocols. Lelantus Spark discuss the broad improvements that both provide over the current Monero protocol and which structural changes from Monero to Spark Seraphis enable these. Dr. Aram will also discuss the main pain points of these protocols and look into possible future improvement ideas. Please help me welcome Aram.
Thank you. Hi everyone, I am Aram Jivanyan. I'm cryptography at Firo. And first want to thank you organizers for inviting me today. I'm really happy to be here and talk more about Lelantus Spark, which is our confidential payment protocol designed jointly with Aram and with an important contribution and feedback from Ko, Luke, and Nicholas. So today we will discuss the main privacy and user experience features of the protocol. We will briefly discuss its security model, formal security model, and we'll also look at its performance characteristics. And then we will discuss few potential future improvement proposals and open research questions. So Lelantus has been designed in 2019, and since then has been used by few cryptocurrency projects such as Firo and Beam. And I believe it has inspired also the design of other privacy protocols such as Lelantus Mimblewimble, Triptych, and Seraphis. The initial version of Lelantus allowed to scale the anonymity set size to thousands of thousands decoy coins. It allowed also to prevent confidentiality of amounts, but it lacked a significant, very important privacy feature, recipient privacy. So Spark is fixing this with very interesting addressing scheme, which not only ensures recipient privacy, but also makes the protocol more, let's say, hardware wallet friendly. It supports multi-signature operations. It provides more granular control over the coins and transactions. So let's see how it works. The addressing scheme, like in this scheme, the user's secret is composed of 3 functional components, which in turn are used to derive 3 different keys. The first one is called incoming viewing key. The incoming viewing key first allows to generate public addresses, diversified public addresses, which can be shared with recipients in order to receive transactions. But it also has to scan the ledger and identify all incoming transactions sent to any diversified address generated with this key. The second one is called full viewing key. This one allows to track not only incoming but also outgoing transactions, so you can track when the certain coin has been spent and maintain the actual wallet balance. And most importantly, this key is used to perform the most computationally heavy operations of the spent transaction generation process, which means that this key can be stored on less trusted but more powerful devices, such as on desktop wallets, while the last key, called spending key, which is used only for very lightweight operations to just finalize the ownership proofs, it can be stored on hardware wallets. And the last part, which is used to generate the spending key, can be generated, can be derived by multi-signature operations. These some rows, you see the bold rows on this diagram, they show that the components are not explicitly part of the key, but they are used in a committed form. And cryptographic commitment basically is the fundamental building block of the protocol, and all sub-protocols which are composing Spark, such as parallel one out of many proofs or range proofs or generalized Chown-Peterson proofs, they are all working with Peterson commitments. And Spark is working in UTXO model, like the users are minting and burning coins. Every coin is composed of separated value commitment and serial commitment, unlike the original Lelantus coins, which have more monolithic structure. And coins can be created by mint and spend transactions. Mint is used to transfer the base layer coins to the shielded layer and also shield the new supply generated by the Coinbase transactions. And spend is the spend transaction is the one which can consume previously minted coins and generate new coins. Let's go into some details of this transaction algorithm. Let's discuss on a regular example which consumes two inputs and creates two new outputs. All inputs should be referred to a certain anonymity set. And during the spend transaction, first creates two offset commitments, one for the value of the original coin and the second one for the serial. These commitments are encoding the same value encoded in the original coins, but are blinded, blinded, so they cannot be linked with the original ones. And spend transaction generates a special membership proof showing that this pair of commitment is actually corresponding to one of the coins in the anonymity set without revealing the link. Next, the transaction creates the new coins, the value commitment and serial commitment. And after having the value commitments, it provides a zero knowledge balance proof, along with a range proof to ensure that no output coin will contain a negative value. At last, it reveals the linking tags of the spent coins, which are used to prevent double spending, and also they are used to generate the ownership proofs through generalized Chow-Peterson algorithms. Tags, linking tags, they play an important role to prevent double spending and also to prove the ownership. So they are kind of derived from the coin serial number. Actually, the value SI in these formulas, the same value which is encoded also in the serial number commitment. And then the Chow-Peterson proofs are sigma protocols which can help to prove that these two commitments are encoding the same values, the same serial number. The original Chow-Peterson proof, which allowed to ensure the discrete logarithm equality, the generalized version allows to prove the relevance of certain exponent in most generic commitments, and also it allows to generate multiple assertion with a more optimized proof. And the Chow-Peterson proof is quite similar to Schnorr signature or Schnorr-like protocols. This is what allows us also to support multi-signature operations. For multi-signature, we provide modified key generation and authorization proof algorithms. But what is most important is these new addresses and spend proofs are totally indistinguishable from the original ones. And also, it doesn't require any trusted dealer to support these operations. We are using different techniques from the well-known Frost and the Music multi-signature protocols designed for Schnorr signatures. Let's also discuss how we maintain the anonymity sets. Like, coins are added incrementally to a global pool of coins, and we logically divide the global pool into anonymity sets of fixed size. Like, potentially it can grow up to 65K. And instead of starting the second set immediately, we started by shifting left the starting point by, let's say, 60,000 coins, just to make sure that no new started anonymity set will be empty enough and it will have enough coins to provide high enough anonymity. So this way, the anonymity sets will follow to each other, and each spend proof should be generated and should explicitly refer to a concrete anonymity set. For example, the first two proofs here are referring to the first set, and the first proof is referring to the fourth anonymity set. This is important also to optimize the verification of transactions. The most heavy part of verifying Spark transaction is the verification of this one out of many proofs, which in turn is boiling down to checking large multi-exponentation operations. And in this multi-exponentation, the generator points are basically the commitments in the anonymity set. So assuming we have two proofs, each referring to the same anonymity set, this verification part, which is using this multi-exponentation, will use the same generator points, right? Which will allow us to combine them mathematically and basically verify two proofs together with a single multi-exponentation. These techniques allows us to have very optimized batch verification of transactions. And this table just shows some numbers that with current benchmarks, I believe there is still some room for engineering optimization, but the current state is that with respect, while keeping the anonymity set size of 65K, the transactions will be about 6 kilobyte. The proving time will take 6 seconds. Verification of a single transaction will be about 860 milliseconds. But you can see that the verification of page of size, let's say 100, the marginal cost of a single transaction verification will be down to 30 milliseconds, 31 milliseconds. Yeah, I also want to mention that the protocols comes with full formal security proofs. We are using the security framework first designed and used by Zero-Cash protocol, which models a very robust framework where adversaries are permitted to add malicious coins into transactions, into anonymity sets, control the choice of transaction inputs, and add arbitrary transactions to the ledger itself. And in this framework, we formally prove that the Sparks ensures 3 security properties, which are the balance property, ledger indistinguishability property, and transaction non-malleability. The first one means that no adversary can alter the user's transactions and cannot redirect the outputs before the transaction is added to the ledger. Ledger indistinguishability basically captures both the anonymity and confidentiality properties of the transaction. It basically proves that no adversary can learn more than what is publicly revealed on the ledger. And balance property ensures that no adversary has spent or can spend more coins than he has minted or received. Yeah, this is about Spark, and regarding to future improvements, we now are looking to replace the membership proofs with more efficient and innovative and membership proofs called curve trees, as has been discussed yesterday by Go. So the most heavy part of Spark transaction are remaining this parallel one out of many proofs. Why parallel one out of many proofs? Because the mechanics of our Spark shows that the coins have been composed of 2 different serial commitments, right? So we have to prove that given a set of pair of commitments and given these offset commitments, both offset commitments are encoding the same value as one of the pairs in the anonymity set. Curve trees are very efficient membership proofs, and we hope that they can be used as a replacement for one out of many proofs, as long as we will find a way to implement parallel version of curve trees so that it can work with pairs of commitments, or we will figure out how to engineer the structure of our coins in order to work with this regular curve trees. Another interesting open research question that we have on our table at this moment is researching page proving method for curve trees. This is actually inspired by another original work that we did at Firo called hierarchical one out of many proofs, and that which allowed us to decrease the proving time. Actually not proving time, but to enable a very efficient page proving techniques. And it remains an open, interesting research question whether we can implement something similar in curve trees to optimize proof generation. Because like in practice, like in spend transaction, you always had to generate proofs for at least two inputs. Oh, that's it. It was quick. Questions? Thank you.
Any audience questions? I think that's it. Thank you, Aram.
Thank you.